Hi there, and welcome to another video about circuit analysis and the basis. Okay, so before we get into problems and solving those problems, we gotta talk about Kirchhoff current law and Kirchhoff voltage law, which are basically summarized here, because those two laws are really, really important for circuit analysis. So basically, what I want to say is that, okay, let's start with the Kirchhoff's current law, which is also called the first law, and then we're going to go to Kirchhoff voltage law, which is also called Kirchhoff second law. Well, Kirchhoff, I don't know, I never managed to get the pronunciation right. I'm just gonna stick with Kirchhoff because I think it's called this way, but whatever. Anyway, Kirchhoff current law. The law basically states that the algebraic sum of currents in a network of conductors meeting at a point is zero. So basically, the sum of k from 1 to n of ik is equal to 0, where n, in this case, is the total number of branches with a current flowing towards or away from the node. Now, this can also be expressed in another way, and we can actually say that the sum of the current entering a node is equal to the sum of the current going out from that node. So the sum of those who get into a node is equal to the sum of those going out of the node. So I draw a little circuit here, which I left open by purpose because, we're just gonna be looking at a single point, but this could be anything, literally anything. We have a power supply here, perhaps we have resistance and other parts of the circuit. There might be some other things here. This could be anything like light bulb or whatever, and here we don't really know. But let's say that I want to apply Kirchhoff first law to this node. Well, I'm just going to, as you can basically see, well, you're going to have a convention. So you're going to have to choose a convention, stick with this convention. So you're going to basically have to choose whether you're going to be considering the one entering and or the one exiting that node as positive or negative, and be consistent every time you do that along your circuit. So let's suppose that we want to do it here. Here I would have, let's see, we have, I don't know, a power supply here and other things. I'm going to have the current entering this node, which is going to be I1. Let's say that from here, the current is going to get into this node as well. So we have I2. But then we're going to have the current to keep flowing and go out from this node up to this, which could be a light bulb. And from here, going down to, honestly, anything, like whatever, doesn't matter. Could be anything, could be a resistance here, inductance, whatever. So we can actually say this in two ways. And the first one is that the sum of the current entering a node is equal to the sum of the current going out from this node, which basically means that I can write I1 plus I2 equal to, well, I3 plus, oops, I didn't, I4, this is I4, plus I4. Like, that's it. The sum of the current entering a node is equal to the sum of the current exiting a node. Conservation of energy, just like that. But this is generally not very useful. It's actually more useful to write it like in the definition, the main definition. So the algebraic sum of currents in a network of conductors meeting at a point is 0. So let's suppose that we're going to consider the current entering a node as positive and those exiting the node as negative. Well, then, if we apply this definition, we're going to have that I1 plus I2 minus I3, because it's exiting the node, minus I4 is going to be equal to 0. And this is a very important statement because, you know, yeah, you could argue that you could say, okay, I'm just gonna bring this one here and this one here and bring it equal to 0 and that's it. And yeah, it's just exactly what I've done. But still, this is a very important statement because around, basically around this, we can solve and find the currents or in a node along our circuits and solve various problems. So this is actually a very important statement. And I'm gonna make some examples later on, but in real problems in another video though. The Kirchhoff second law, so the Kirchhoff voltage law instead, says that the directed sum of the potential differences, which is just voltages, around any closed loop is 0. So it's basically the sum from k equal 1 to n of vk equal to 0, where n in this case is the total number of voltages measured. So let's suppose that we have a circuit here. There could be more things, doesn't matter. Yeah, this time is closed because, you know, I need a closed loop. So I had to write it close. But, you know, just like this one, it could be anything. Like here, could be attached anything. Other resistances, doesn't matter. So let's just say that we have a power supply and the current is flowing in perhaps in this direction, but and gonna go here, here, and so on. So the fact that let's just have there could be more things here, like an extension of this circuit, but in this case we're gonna choose this as our closed loop. Okay, so this one is our closed loop. So I'm not going to include R4, this resistance here. It doesn't matter, I don't want this, I'm not considering this. So since this is a closed loop, the Kirchhoff second law, so the Kirchhoff voltage law, is saying that the directed sum of the potential differences around any closed loop is 0. So this actually means that the voltages, the sum of the voltages in this closed loop is going to be equal to 0, which is like saying that V1 plus V2 plus V3 plus V4 is going to be equal to 0. And this is a very important statement as well. Because thanks to this we can, as I said, get closed loop of our circuits, which, as I said, doesn't matter, and could be there could be a very large circuit. There could be anything here attached here, but if I just consider this closed loop of all my circuit, I can say that the sum of the currents, or the sum of the voltages around this closed loop, it's going to be equal to 0. So v1 plus v2 plus v3 plus v4 must be equal to 0. And this is a very, very important statement as well. So why are those two statements important? Well, you're gonna see it when I'm gonna be solving circuits, and I'm gonna be doing it very, very soon in the next video, right in the next video. And I'm just gonna be using Kirchhoff laws. So you're gonna see why those two are important. Well, I'm actually pretty, I didn't actually give you the full picture here. I mean, I just spent like 10-11 minutes talking about Kirchhoff laws, but I didn't actually mention many things. Many professors will actually argue that this is not a lecture, this is not an explanation, a satisfying explanation, and it probably isn't. But this is like the very basic. Like the reason why I recorded this is as to give you the very basics. So you just have to know that this is the basic stuff, and this is what you need right now to solve the very basic circuit. So this is just the idea behind those two laws. But there could be there is much more behind this. In particular, for the voltage law. If you're interested in the voltage law, please go watch the Feynman lecture about Kirchhoff voltage law, because it's actually very interesting. And yeah, if you're interested and you want to know more, go and read the papers and search for the Feynman lecture, because honestly it's very well done. It's going to be use integrals to explain this, and make references about Maxwell equations, and yeah, it's very interesting. Go, really do check it out. But I won't be discussing Feynman lecture here. The Feynman lecture and the way Feynman explained this, because it's behind. It's not the point of what I'm trying to say. So do check it out, and then come back here and watch the next video for how to solve problems using those two laws.